Okay, so it gives me very great pleasure to introduce somebody who really doesn't need any introduction to this audience, Dr. Sam Devlin. If I could come up with 3 things that would summarise Sam, they would be York. He's been in York forever, all the way through undergraduate, PhD, postdoc, and now a fellowship and lectureship in the DC Hub. It will be machine learning, and that's going to be part of the talk today, and games, where among Sam's many lesser-known triumphs are wins in hackathons and game jams, and one particular memorable game a few years ago where he won the top prize in the York Global Game Jam. Okay, so.
Thank you. So, as Peter said, today we're going to be talking about machine learning and its applications in games, particularly looking at general game playing agents. So agents that don't just play one game, but can play a whole range of games with the same background. To motivate this a little bit, I'm just going to go through the history of games a little bit and where AI has sort of interceded with that. Starting with a game that we've been playing for about 3,000 years now, called Go. So this is played on a 19 by 19 board between 2 players. It's a fully observable game. You take turns to place black and white stones. Because it's a 19 by 19 board and you can place a stone on any free spot, there's a branching factor of 250 on this game. Effectively, this means there's a crazy number of legal game positions in this game, right? You couldn't enumerate every situation, everything you should do in every state. So unlike some of the other AI methods we'll see, there's a lot of machine learning in the method that was developed for this. And last month, Google DeepMind announced that they'd beaten a European champion at Go. Okay, this is a huge breakthrough for game AI. It got the front, not just a paper in Nature, but it got the front cover of Nature with this outcome. And next month they're playing against a world champion, Lee Sedol. It's all going to be televised live, 5-game series from 9th of March to the 15th of March. If they can be a world champion, this is a breakthrough in game AI that many experts in the field thought we were a decade away from doing. Okay, this is a real big advance in this space. Moving forward a few thousand years, humans started playing chess around the 6th century. There's an interesting trend. As we go through history, the games humans play tend to get simpler, right? So the AIs beat the world champion in 1997. This was IBM DeepBlue system beating Garry Kasparov, the world champion at the time. Moving on to 13th century, we've got even easier in the games, and we started playing checkers. And in 1994, Jonathan Chafin's team beat the human world champion, Marion Tinsley. And then later on in 2007, they did exactly that. They enumerated every single state and solved the game. Okay, so if both people play checkers perfectly, the game is a draw. And that the publication of that result was in a science publication. Moving on to about the 1800s, we started playing poker, and there was a big breakthrough in the AI for this last year. Again, a publication in Science by Michael Bowling's team in Alberta, where they've essentially solved one variant, although the poker experts in the room, Mark, tell me that this is one very simple version, so they've got some work to go. But they've got great stuff going on in Alberta in different versions of poker through this. And then TVs came into our lives, and we started playing some very different games. Okay, so the Jeopardy, the TV show where you try to guess what the question is for a particular answer that's given. Humans have been playing this since about the 1960s, and IBM again with Watson beat the human world champions in 2011 at this game. And then in the 1970s, to get really into the sort of digital game space that I'm interested in, humans started playing in Atari 2600. Okay, and again from Google DeepMind, a great paper last year in Nature on achieving human-level control across a whole range of games. So the bars here for the AI behaving above human-level performance. In a whole range of these games, this one system can outplay humans in a whole bunch of them. This is actually a GIF of it learning. And so what it learns is this nice strategy where it fires the ball above the top and then just clears the top of the level. Okay.
Who are the authors?
It's Google DeepMind. Yeah, there's quite a list of authors. David Silver, Demis Hassabis, teams of engineers, but a great result. So around this time, the digital game industry was booming from 1970s to about 1983. Unfortunately, this game came out in 1982. This is E.T. for the Atari, and it's widely accredited as the worst game of all time. This nearly caused the collapse of the entire digital games industry. To the extent that there's a rumour that Atari apparently tried to bury all the excess stock in a landfill site in one of the southern states in America. Great documentary on this if people are interested. Won't spoil it as to whether they found it or not. But things changed. 1985, the Nintendo Entertainment System came out, and Nintendo countered this flood on the market of poor quality games that was going on in Atari and what ET is representative of, by being much more strict about the games that got onto the platform, and giving the official Nintendo seal to only games that they approved to go on there. And they had their iconic Mario, and as we'll see later on, we're at a state now where we can learn how to play that specific game, and again we can make domain-specific AIs for Mario games. The interesting thing about this computer was it actually came with its own general game-playing agent. This is Rob, or Robotic Operating Buddy. He could play a couple of games with you. By all accounts, he was fairly terrible. So this isn't the sort of level of general game-playing agent that we're going for, but nice to see that they were trying in the 80s. And so this is the state of the art. Okay, this is a paper by Google DeepMind that came out in the last couple of weeks, I think. And they're now able to play sort of early 1990s 3D games from just looking at the pixels on the screen and control, in this case, the car and the Torque's car simulator engine. Okay, so they're just looking at the pixels on the screen and getting a reward for the proportional to the velocity that they're moving along the actual track. And so it can learn quite complex behaviours for that, and the same architecture is used on this, is used on the Atari games, is used on another 3D game from about this era of finding its way through random mazes and learning a general policy that can map to different mazes. But this is modern commercial games, okay? And so things have moved along a lot since the 1990s, and there's a whole range of challenges there of increasing complexity to bring us from being able to play 1990s games to being able to play modern games. I highlight these two in particular. So Total War Rome 2 by Creative Assembly came out about 2 years ago. They've talked publicly about the use of Monte Carlo tree search, some of the algorithms that we work with here, and have been used in some of those previous examples to play very specific parts of these games, okay? So we can't develop AIs that can learn to play these games entirely, but very specific parts we can. Similarly, Fable Legends have talked publicly about their use of Monte Carlo tree search in a game that's currently in open beta and will be released later this year. So what's just as a small aside, the industry's booming now. Okay, there's some analysis that was done on the NEMOG project that I was on for the last 2 years that was looking at new economic models and opportunities for digital games. So it's a bit of analysis for the industry. It's roughly employing about 30,000 people in the UK within the games industry and has a turnover of about £40 million a year. The reason I mention this is that this is a huge opportunity for the whole department to have impact on an industry that reaches millions of people across the country. Okay, we have great contacts with the industry through NEMOG, through IGI, through the DC Hub, and through some of the academics in the room that have been working with the industry for quite some time now. I spent a little time in preparation of this talk going through the research groups for every group in the department, and I think there are as open challenges in the industry that every single group in the department could be dealing with. Okay, people will say that games are just something that teenage boys play, right? But the average gamer is now in their 30s, right? The demographics have changed. It's now 50-50 guys and girls. Okay, if you can get your tech into games, you can reach millions of people of a very widespread demographic. You've got good economic impact potential, good social impact potential. Yeah. But that's not what I want to focus on. I want to focus on what are the unsolved issues, or at least a small set of the unsolved issues in game playing AI, and the ones that the work I'm going to present today particularly tries to address. So the first is general game playing, which is playing lots of different games instead of one, as I started the talk on. And as the talk developed, I started getting into more and more things and going down a bit of a rabbit hole of, well, if you're going to play a whole range of games, there's always going to be that one game that has really complex game mechanics, and how would you solve that one? And in particular, one complex game mechanic is social games, and having to deal with talking to people and how you deal with that, and whether you can make the agent be more believable. And then one real technical issue is that a lot of these games have very sparse rewards. And because we transfer our knowledge from previous games and other things we've played, we can overcome that. But if the agent's just learning fresh on that instance, a sparse reward problem can be a very big issue in learning how to play that game. So to go a bit more specific, for general game playing, there's 3 very popular platforms out there. Stanford run a competition, which is mostly based on board games, digital version, so you can develop an agent, but board games. This one in the middle is the general video game AI competition. So this is aimed at sort of arcade level games. And then on the far side, we have the arcade learning environment, which is the Atari 2600 games that DeepMind have done so well on. So all of these provide you with a real range of games that you can play, rather than just trying to focus on one. So if you develop an agent for it, it can play across all the games and really test its ability across a variety of problems. Since things have moved on a little from 1990s just driving around a track, some of the game mechanics we're employing now are far more complex than just driving around a fixed track. I highlight here a sort of version of Portal. This is a 3D environment puzzle game where you can shoot your portal gun at 2 spaces on a level and be able to warp from one place to the other. Okay, solving the puzzles in this requires a lot of very difficult spatial reasoning and understanding momentum, and there's a lot of physics that you have to model internally to understand how to be able to pass these levels. But it's a fascinating control problem as to how you would overcome this and how you could learn to overcome this. Another complex game mechanic, though, as I said, is the social aspect. So I note 2 here of the Resistance and Coup, which are 2 quite popular board games around the room. I've seen quite a few people play these. These are games with hidden roles where the actual mechanic of the game is very simple. You just take turns voting on who you think's in certain roles. But it's all about deception and hiding your role, and it's so much more in the social interactions between people of them discussing and accusing each other and trying to figure out who is on which side and who's done what and who hasn't done something. Okay, so building an agent for this is very difficult. There are some examples of it, but making it believable and actually act like a human player is quite challenging. There was a competition for a few years that ran with a similar aim using Unreal Tournament 2004, and the idea here was to develop agents that could act, could pass as a human player. So you had experts watch the bots and watch humans, and could they tell the difference? So kind of a relaxed form of the Turing test. The difficulty was, though, that if the only way you can express yourself is through your movement within a 3D space, then it's quite hard to tell the difference between an AI and a human player. It's a relatively simple problem if your expressivity is lowered. The difficulty of the Turing test is we allow the agents to have natural language, and by having natural language, there's a lot of ways we can express ourselves, and a lot of ways that an AI can give away the fact that it's a computer program and not a human being. So trying to build believable agents that play like humans, definitely a challenging issue, but considerably less than Turing test. I'm not trying to solve Turing test right now, but a nice step towards it maybe. And the final one is sparse rewards. So this comes back again and links in with the complex game mechanics, because this is Montezuma's Revenge for the Atari. And this is already the level of complex mechanics that can throw up some of these systems. So Google DeepMind system cannot play this, or at least it could in the Nature paper last year, but I suspect they might have something by now, because this is something that can be overcome. The issue here is that the little man in the center of the room there needs to jump over to the ledge on the right, climb down the ladder, wait for the rolling skull to approach him, jump over that without hitting his head on the spiky barbed wire, go down the steps, up the stairs, and collect the key before he'll get a reward. So he has to learn a very long sequence of actions before it will get any reward, any signal that it's doing the right thing. And so overcoming that sparsity in the reward signal is very challenging for these agents. So I've identified 4 unsolved issues of how to play lots of games rather than one, the complexity of the game mechanics in some of these modern games, how to play social games and be more believable, more human-like, and then this issue of having sparse rewards. And so my proposed approach to dealing with this is, and we're going to go step through each one of these now and go into a bit more detail, is to first build a game-playing agent. Okay, if we can't play one game, we can't play lots of games. It's fairly simple. Then to overcome complex game mechanics, we can learn from a better agent how to play those games. So if there's another agent out there that can already play those games, and there are, then we can learn from them and use that to effectively bootstrap our own approach. And then to become believable agents and more human-like, let's learn from lots of better agents. I'm going to be vague here because it'll become clearer as the talk goes on. Finally, for the sparse rewards one, the way that we're going to learn from agents is going to help us to overcome that sparse rewards issue as well. Okay. So let's build a game-playing agent. Okay. So this is coming from the reinforcement learning literature. It's from Sutton and Bartow's book of this concept of having an agent acting within an environment. So for us, the agent is the AI that's trying to play the game. The environment is the game. Okay. From the game, the agent gets what's the current state of the game. Now this can be in like DeepMind's work, it can be the screenshot, or if you've got access to the game engine, it can actually be where certain features are, so a labeled instance of where the assets are. The agent then takes an action. The environment updates the state, gives the new state, and it gives the agent some sort of reward. Now that reward might be very sparse, as we've discussed, or it could be more informative depending on how we design our environment or the other agents that we might learn from. The agent then has to learn to maximize the discounted sum of these rewards over time. Okay. Formally, we model this environment, which is our game, as a Markov decision process, usually, or if in a lot of games it will be a partially observable Markov decision process because you can't see the full game state, you can just see your view. Especially this works if you're just taking the pixels on the screen, you're only seeing that, you're not seeing the whole virtual environment. And then if you put lots of these game-playing agents in the environment, you get a decentralized, partially observable Markov decision process, which coincidentally we have Franz Ollyhoek coming in on the 4th of May. He's coming over from the University of Liverpool. He's an expert in decentralized POM-DPs and the algorithms on how you solve them. So he's coming to give the departmental seminar on 4th of May. I highly recommend that to find out more on that. But it's going back to the sort of single agent and the partially observable MDP, there's 2 big algorithms that are proving very successful in this space at the moment. Yep.
So one question I'm not clear about running through all this, when you build the general agent,
Yep.
how much does it know is built into it or told the rules of a particular game it's engaging?
Ideally, none, but as this slide will show, it depends on the implementation. Okay, so with a Monte Carlo tree search approach, if you take it as a typical planning algorithm, you need to have some knowledge. So planning algorithms typically have knowledge of the transition function. If I'm in this state, I take this action, what's the probability distribution over what next state I'll be in? Okay, you need that to be able to do simulation in a Monte Carlo tree search or a planning algorithm. However, if your simulation in a virtual environment is just running through the game logic and playing the game out, the similarities between these Monte Carlo tree search and reinforcement learning are very similar. So ideally we don't build it in, and especially for when MCTS is applied for the GVG AI competition, it doesn't know that. It has a way of simulating forwards in time, but it doesn't know the rules of the game. With the DeepQ side, all it's getting is pixels on the screen and a reward signal. Okay, so no knowledge of the game, just pixels on the screen and a reward signal. Okay.
What about that Atari case?
Just pixels on the screen and a reward signal.
The one with going down a ladder and across?
Just pixels and thing, but then it doesn't learn it. So yeah, so they are using that, but not giving it knowledge of the game, but then that doesn't work. Which is where I think they've probably solved the game, because you could build in knowledge of the game and overcome Montezuma's revenge.
You gotta learn the game and the strategy.
Well, that depends if you take a model-free or a model-based approach, right? So yeah, a model-based approach might work better there if you learn the transition function as you progress. Anyway, so yeah, these two algorithms are the two big ones at the moment in this space. So Monte Carlo tree search, as I said, has been very successful in the GVG AI competition. So this was the arcade-style games. And then the DeepQ, in particular popularized by Google DeepMind, has been successful in the arcade learning environment, which was the Atari games. There is a separation in principle between these, one being a planning algorithm and one being a reinforcement learning algorithm. But as I said, when you're acting in a virtual environment, if your rollout stage in your simulation is just the game logic, then there's an equivalence here. And I don't want to go too much into those details because really these are just sequential decision-making algorithms. And there's a theorem of what a universal AI in these spaces is. So this is the optimal universal AI in that space. And anything else we do is an approximation of this. And we have to approximate this because it's intractable to compute this for all games, okay? So this is Marcus Hutter's work on universal AI. Really interesting if people want to go deep on theoretical AI stuff. But I'm going to take the presumption similar to what Nick Bostrom's work talks about and assume that we have that, okay? So we do. We have implementations of MCTS. Some have been developed here at York very well by Peter and previous projects. And we've got access to implementations of the DeepQ network and the infrastructure to run that, okay? So we assume we've got that ability for an agent to learn in an environment, but how do we control it, okay? Nick Bostrom is a philosopher from Oxford who wrote this book, Superintelligence. Fascinating book, well worth reading. Also did a TED Talk. If you're lazier, watch the TED Talk. It's a good intro. But he argues that we could spend forever thinking about how to build an AI, but if we don't know how to control one when we get here, it might be too late. Okay, so issues of motivation selection and value loading into an agent are critical for us to start exploring now and understanding, okay? Because by the time we build an AI or a true artificial general intelligence, the rate that it'll improve could be too quick for us to deal with. So I'm going to focus a little bit on the control problem within this concept of building an agent that can play a single game. And so the specific game that I started off with, and this is going back to PhD work, was simulated robotic soccer, okay? It didn't look like that. It looked a bit more like that, but that doesn't blow up well to a screen size. So specifically what we had is the two red agents are takers, and they're trying to learn how to take possession of the ball off the free agents, keeping possession of the ball within a fixed boundary. Okay, so they want to minimize the amount of time that the keepers keep possession of the ball, and the actions they can do is they can either mark one of the players or they can dive in for a tackle on someone. Now, if we just leave them to learn in this environment, if we start them off tabula rasa with no prior knowledge of the environment, they take a very long time to learn quite a rubbish performance. Okay, if we instead use some heuristic knowledge that we know, we can improve the performance. So in this case, when we watch them learn, the takers would follow each other around and just effectively do the same policy as each other. Okay, I'm not very good at football. But even I know that you should spread out a little bit, okay? So this is a bit of heuristic knowledge that we had. So we can give that extra knowledge through the reward signal, okay? So this is starting to counter that sparse reward, because the only reward these are getting is once the ball goes off, then they get rewarded for managing to kick the ball off the pitch. So if we give additional rewards to encourage separation, the difficulty comes in that might become the goal for the agents, okay? They might just run to the corners of the pitch and hide from the ball, okay? Because they're getting that extra reward and they get a beneficial cycle from just separating. So as part of my PhD work with Daniel Kodenko, we proved that if you give the additional reward in this specific format, that you don't change what the goal of the system is, okay? So the goal of the system remains win possession of the ball as quickly as possible, but you get this extra reward of saying spread out. And what you get is, so we've got down the bottom how long it was taken to train, and then the episode duration on the side. And so smaller is better. Base learner with no prior knowledge, like I said, it takes a long time to learn something that's not very good. And then when you encourage it to separate, or if you encourage one to be the tackler and one to be the marker, then we get a significant improvement in the performance of the agent by providing that heuristic knowledge. Downside is this is very domain specific. Okay, this spreading out thing does not work if we're trying to play Montezuma's Revenge, if we're trying to play Portal. Okay, so in one of my rare occasions of leaving York, I went to Oregon State University for a summer to explore difference rewards, which is an area that they're particularly known for, the group over there with Khan Tuma. And so this is a way of rewarding cooperative multi-agent teams by their actual contribution to the system. Okay, so rather than giving them the global reward, which is how long did it take us to win possession of the ball, you only reward them the difference in what the global reward was and what it would have been if they hadn't taken part. So they get rewarded their contribution. Okay, so for a football example, this would be if the team scores a goal, typically with a global reward, everybody gets rewarded for scoring the goal. But one of the players might have been staring at the goalpost or something. It might not have been contributing at all. But if we can separate out what contribution they are, we only reward the goal scorer, or we only reward the players that actually participated in scoring the goal, then we can get significantly better performance. And so there were some issues with difference rewards. It's very unclear about the theoretical guarantees. So they might alter the Nash equilibria, whereas our methods didn't. So the work I did there was to combine them and develop a version of this that did have the theoretical guarantees. Now, this is more general. It applies to all cooperative multi-agent systems, and it's been shown in a whole range of these to be very beneficial. But it is just cooperative multi-agent systems, so this wouldn't work in Go, for instance, where it's a fully competitive game. And so through theorems like no free lunch, then there's presumably no one heuristic that we could apply that would allow agents to play better across all games. But there are some agents out there that can play all games. Okay, so step 2, learn from a better game-playing agent. And the better game-playing agent in this case is us. Okay, by the age of 18, the average person has played 10,000 hours of games. Okay, that's enough to be, according to certain theories, it's enough to be a virtuoso in saying. Okay, so why don't we learn from humans on how to play games? Okay, if we're going to build a general game-playing agent, let's learn from humans and then potentially improve upon it. Now, the average 18-year-old, I reckon, could tell if an agent was playing badly or not. It could look at Montezuma's Revenge and say, no, it's just bouncing its head against the spiky pole. I don't think, hopefully, that they'd be able to do potential-based reward shaping. Otherwise, I did my PhD about 10 years late. So what we need is a way to learn from an arbitrary reward signal. So I copped out a little bit here. There's a lot of maths in these two papers, and I really wanted to make it clear as well about where credit is on this one. So in 2012, Daniel and myself extended the potential-based reward shaping proofs that we talked about before to allow for the potential function to change online. So the knowledge that you're shaping for can change whilst the agent's learning. So you might decide partway through a game that actually spreading out isn't a good idea. You should be sticking together. And you can keep changing the rewards you give the agent, but still maintain the guarantees that it will learn something that was the initial reward signal policy. And then I met Anna, who's from Anne Noé's group in Vrije Université, Brussels. And she had this idea about how we could, using that underlying theory, automatically translate any reward function. So regardless of how someone's specifying the reward function, we can transform that into potential-based reward shaping with a dynamic potential function and maintain the same guarantees. Okay? This means that someone can just sit there and give advice, go good, bad, and the agent will still learn what it should learn, but it will learn better because of that input from players. Okay? There's a lot to take in, especially from a slide with just 2 paper references, but thankfully they took the effort to put together a video of this for playing Mario. So on the left here, we have the agent that's learning tabula rasa. It's got no prior knowledge. All it's getting is the reward signal from the game. So it gets points when it kills an enemy or when it gets coins and so forth. Whereas the one on the right has someone sit there just clicking every now and again, yeah, that looks okay, that looks bad, that looks okay. And so it can learn a lot quicker. And as you can see, it's already further along in the level, and this is seconds of learning as opposed to what would take hours if we were to use the one on the left. The nice thing here as well is that if someone was sat there trying to put this agent off and was giving it really bad advice, so every time it goes left it rewarded it, the agent would follow that first and it would learn slower, but it would still be guaranteed to learn the optimal policy over time. Okay? So by this stage, we can now learn how to play games, and we can train them to play some more complex mechanics than it'd be able to learn on its own. But it's only ever going to play with that sort of system in a game style that we've thought about, right? So if we've designed the game and we want the AI to play in a specific way, we can make it play that way by using this system. But we can't capture play styles that we don't foresee with it. Okay, so my motivating example here, so next step, and this is the learning from more agents step, is to capture emergent play styles. So my motivating example comes from Counter-Strike that I learned last night that I was playing at probably a too young a age. So please ignore the knife in the hand. So in this game, so this was based on the Quake 2 engine. There was an exploit within the physics, so there's a bug in the physics that meant that if you moved in this slightly obscure behaviour of quickly twisting the mouse as you jump and strafing left and right, you could move considerably faster than you should be able to. Okay, so this is slightly demonstrating it. It's hard to get grips of without there being other players in there, unfortunately, but in team-based competitive online games like this was a huge advantage. And for this work, the main thing that I use this as a motivating example is that we wouldn't have developed an AI to play like that, okay? Because it wasn't something as a designer of the game that was intended to happen. But when you were playing this game online at the time, as soon as someone did that, you knew you weren't playing against an AI. You knew you were playing against a human because the AIs didn't know how to do it yet. But if we could set up a system that automatically monitored how people are playing, we could capture that. Okay, we could recognize that that's happening, and then either as a designer make a decision and say that's a bug in the code and it shouldn't be happening, so we can try and find the bug and fix it and stop players from playing like it, or we can start biasing the AI to play like it. Okay, so games have always generated data, digital games in particular, but now due to a ubiquitous presence of the internet, we can collect that data. Okay, in particular, there's a trend in the industry towards cloud gaming. Either having cloud as the back end so that you can scale up your game to lots of players very quickly, or even to the extent of playing the game on a remote server and then just streaming the video and using the local machine to just send inputs and display the video. My colleagues on the NEMOG project from the business schools will tell you that this potentially has a highly disruptive effect on the industry, right? This could change the whole console cycle. It could stop us having to keep doing that iterative things because all the hardware could be upgraded server side rather than client side. But that's getting into the business side. The thing that I really want to focus here on is that this technology enables us now to routinely collect gameplay trace level data. Okay? It is feasible from most of these games now to collect everywhere you click in the game, every action you make, every decision, right down to clicks, everything that gets done, where you move your mouse, where you hold it over for a little while. We can capture all of that data, and that's a very powerful source of information. I gave another talk recently for a TEDx event on all the ways that this could be used to answer wider questions of social and scientific importance. Please watch it. If you've got some time, you want to hear me talk some more. So that focused more on broader scientific questions rather than just improving the game design. But here, I want to focus on the game design. So we've got gameplay trace level data. In fact, for one specific example, we have it from AI Factory, a company that make card games for mobile devices. And in particular for their implementation of Spades, which is a bridge-like card game. It's the #1 Spades game on the Google Play Store, over 5 million downloads. I think that's possibly out of date now. Huge number of downloads on this game and a number of players playing it. In this version of the game, you're the player at the bottom there, and you're playing with an AI, Rob, so he's your teammate, and you're playing against Bill and Sarah, who are on the either side, who are also AIs. Okay. We have a lot of details on this in relationship with them because of work that Peter did and Daniel Whitehouse and Ed Powley, who some people will recognise from being around here the last couple of years, and Jeff Rollison there from AI Factory, because between them they developed the AI for this game, and it's the version that's in action in the game. As part of that relationship, AI Factory collected full gameplay traces of a large sample of players, showing how they behaved and how the AI behaved. When we did the analysis on this data, though, we showed that in certain situations, so we've got down here on the left, certain abstract moves that humans or the AI could play, and then we've got counts of how often the human played and how often the AI played. And in certain situations, the AI is playing very differently to how the humans played. Okay, so can we use all this data now to bias our AI towards that play style? And so we built a decision tree model of the human behaviour. So this predicts, with reasonable accuracy, in a given context within a game, what action a human will play. And there's some ongoing work at the moment about using this version to bias players in the game. Now, the downside to this approach is that we amalgamated all the players into one, right? Different people play games differently, okay? Different people play games differently on different days, but we didn't capture that in this model. We put everybody into one predictive model. So what I'm working on at the moment is, instead of doing that at the level of just one decision tree for every player, we now generate a decision tree for every single player. We've generated a similarity matrix of how similar different trees are, and then we cluster on those trees. The reasoning for this is that if we cluster on just the raw moves that a player makes, we'll get clusters of similar moves, but the tree represents the player's play style. And if we can cluster the trees, then we'll find clusters of play style rather than clusters of similar moves. Then a designer can look at this and say, well, so the early results on this show there's about 4 clusters. So a designer can look at 4 representative players and see how they're playing, see if any of them are ones that they want to rule out, and then we can bias the AI for the ones that it doesn't want to rule out towards the different play styles that are emerging. This works particularly well because the game has a very discrete action space, but this is a recurring theme in a lot of games. So a lot of games have these tech trees or progression trees, and you can apply a similar sort of formal clustering to find how people are progressing through these to again find different play styles, and this can be used to inform the designers. Okay. But my final part, I see this as a cycle where the game generates a large amount of data that we can analyze and find these different play styles, and then we can bias the AI within the game. By biasing the AI in the game, we can then improve the game itself. Okay? Now, I've talked a lot about games and not interactive media, but put interactive media in here too, and that's because I know games. But through the DC Hub, and there's a few people around the room, we've got great interaction with TFTV on interactive media, and hopefully we can now start to deploy these agents into other wider forms of interactive media. And again, look at some more ranging versions of social impact by putting these into educational pieces of interactive media, putting them into things for, we're working with the Centre for Digital Heritage, to get these into heritage sites and have them as people to make more engaging experiences at heritage sites, so forth. But yeah, that's my framework, and that's what I'm looking forward to working on whilst on this new role. Thank you.
Any questions?
So you're kind of particularly artificially crippling the vanilla AIs by not telling them the game is not to be played. So the Mario agent just puts it around on the left-hand side of the screen. That's, all of us know that's not what's fun about playing a game, so we can do that.
Yeah, so I think the interesting thing there is, so we can develop better AIs, obviously, by imparting more information on the game.
No, it's not about the game. It's about what games, about games. The concept of the game is not to put around on the left-hand side of the screen for half an hour.
Yep. So
any game. That's not the point of any game.
Yep. So one of the things that I didn't touch on was wanting to work with psychologists, sociologists, and HCI people to understand better how people play games and impart that onto an agent that's learning from itself, so that it knows the basis of what it is to play a game before it starts to act, rather than it footsie around on the left-hand side. So I think there's ways to bring that in. I'm not sure on yep.
So it seems like you've set yourself a task which is much harder, because somebody who doesn't know anything sitting down at Mario will probably need to be told, go to the right.
Yep.
I know that obviously you could experiment totally blind, but you're normally told something, at least usually by the game. And I know there's natural languages used and stuff there, but is there a way to encode the basic rules and then let it learn to play from that?
Well, so in effect, that's what Monte Carlo tree search does by having a forward model, so that it can simulate forwards towards and project what reward it's going to receive, and then base it off of that. But that is also the motivation behind the human version, right? So like you said, you get told, right? I learned a lot of games. I learned Dark Souls through Dave telling me that, you need to keep bashing away at things, and you need to go down here and get this first, right? And so human intervention is the way that I see that happening. But rather than having to have an expert sit down and be able to code that situation, having any game player be able to sit down and go, yeah, that looks good.
Can I just follow up? I know as a chair I probably shouldn't do this, but is there a good way to encode that? So the sort of informal knowledge that somebody might get, like, go and find a dark space in this level, or keep hopping to the right. Is there a good way to encode that?
So one of the things that I'm playing around with, I forget the name of the guy, but it's novelty search. There's a professor in the States. Well, it comes into Schmidhuber's stuff as well, right? So it wasn't Schmidhuber's one that I'm thinking of, but yeah, Schmidhuber has similar things about what it is to be fun and exploring new spaces. And yeah, I think there's some quite general heuristics there that you could use. So I didn't quite touch on it when I got to the general one, but biasing towards novelty and in Schmidhuber's case, biasing towards fun, could encourage that sort of behaviour and it to emerge, rather than having to do something more domain specific.
Mike.
So is better AI actually going to lead to better games? So I guess I've seen people claim from Games Industry people that better AI is kind of pointless because users can't tell the difference. I suppose also thinking of kind of Paul and Alina's stuff about kind of the placebo effect, where if you tell the users that the games are smarter, then they believe that they're smarter, even though they're just sort of imposing their kind of value judgments.
Yep.
So what's the evidence that kind of if your games get smarter, that they're actually going to be more fun or better in any respect?
So I would say the main motivation is for me anyway, was that example with the bunny hopping, that by making things play more like the current player base, then you've got access to a more representative AI, and also as a way that it's reporting them back to the developers from that gameplay trace level data, what they should action, whether they need to fix something or whether they need to design something new.
This is kind of like a gaming development tool rather than a sort of, you're not kind of building bots for the players, you're building kind of a exploration tool for the developers almost.
So I think it could be used in both, right, as a way to keep the bots up to date. So you drop in a vanilla MCTS agent or DeepQ agent, and it plays okay for a while whilst people are joining the game. So you populate a game, because nobody wants to join the online game that's completely empty and has got nobody in there. Right, so you populate it with a bunch of bland MCTS agents. They can play reasonably well because they've got general game playing abilities. Over time, they learn the specific game better by observing humans and start to play more like the styles. But yes, the other side is that it becomes a design tool. So we've had quite a few conversations with games companies that have said they don't know what to do with that gameplay trace level data. Okay. One CEO referred to it as a hose that you can't turn off, like the stuff's flooding in, but they don't know what to do with it, right? But there's huge amounts of insights that could be gained from that, Okay. Games company typically, as far as the analytics, a lot of the work is done at a very high level of metrics. So they just look at daily average users, monthly average users, and so they can work out that lots of people are dropping out of a game at this stage, but they can't work out any sort of causal relationship. And maybe by looking at the different play styles, then we can not find those causal relationships, but we can highlight these are the ways different people are playing. Here's a model of how that person's playing, and then they could look at it and see where the issues are.
Daniel, I think. So you said that you can use observations on how people play to come up with a general game playing agent. I would actually say that there is a problem with that, because when you look at observations how people play, you'll get how they play a specific game.
Yeah.
And that will not necessarily carry over to another game. What would be, I think, more useful is to get data on how people learn to play a game, because through that you see how they explore the action space during the playing. And this exploration, how people explore the action space, could then influence the way that the agent, the AI agent, is exploring the action space when being faced with a completely new game.
Yep.
So it's more how people learn a game. Data on this would be probably more suited for general game AI than how people actually play the game.
Yeah, I do agree that, well, and you want to see the things that are going to transfer, right, between different games. Whereas what I was really proposing here is that the whole framework of having the human in the loop there, it allows you to play multiple games, but it is through developing an AI for a specific game, improving it for that specific game, and then that human in the loop is part of the ability to play generally lots of games. But yeah, if there was a way to abstract what the human's process is so that you can transfer it across different games, then that would be
this would fit
even
very
better.
well with reward shaping, because that's influencing the exploration.
Mm-hmm. Yeah.
So that's we can talk about it later.
So, I mean, if we go back to the Mario example,
Yep.
I mean, and also Paul's question earlier, so is it possible to generalize and abstract and get the system to learn the game physics at a high level, at an abstract level, so that some of that knowledge could then be transported to other games, for example?
As in to learn things like go right.
Go right, notion of the wall, notion of the bridge, etc. So that some sort of game physics,
Yep.
Which we as humans always use,
Yep.
take advantage of.
So you are getting towards model-based methods then, so DynaQ and things that will learn the transition function, and if it understands the transition function, I'm in this state and I hit this and I do this action, then I hit the wall and I don't move further. So yeah, that can be done. The difficulty then comes in transferring that to new games and finding the mapping between two different games that you can do. I think it's one of the things that's quite interesting with the DeepQ network, because of that abstraction to just being pixels on the screen, because all visual games have pixels on the screen, right? So with their state representation, the state representation just transfers naturally, right? So one of the things I think is quite interesting with that Atari work is that they've published the performance on each individual game, but they've got a convolutional net somewhere that's been trained on all of them, right? And they've transferred it. So perhaps even in a model-free space, if your state representation is the same, you could perhaps learn that transfer.
Yeah, so presumably, a deep neural network using lots of hidden latent variables is learning those abstract representations, and hence it is able to generalize better.
So I think this fits really nicely with some of the work Mark's done. So Mark's one of the sociologists in DC Hub about reading different games. In particular, he has a paper on roguelike games and about understanding that certain symbols mean similar things in different games and rarely differentiates. So if we were to train a deep convolutional neural network to play roguelike games, we could, validate Mark's theory and have that crossover, so transfer, and I think it'd be very achievable with a game like that to learn those abstractions and then also to visualize them as well. So when you can visualize the what maximally activates a convolutional layer, I think you'd be able to really see the sorts of patterns that Mark's identified across the games with that. Harder to think what the common patterns to recognise are in some of the more visually expressive games, though. I guess you'd end up learning edge detectors and things again.
Can I just ask one more question about the Counter-Strike AI? So you use that as an example of a human-like behaviour.
Yep.
It feels to me like a button-pushing, state action exploring AI might find that based on the idea that it wants to get around as fast as it possibly can.
Feasible, and I think it might have been an interesting study to do to see if it could find that exploit. It's a very complex range of moves, but yeah, I mean that sort of thing's been done with genetic algorithms, right? So.
Okay.
Cool.
Any other questions? So, to me, thanks, Sam, for an excellent talk.